Now we continue with Tomas Voros. He's going to give his talk about determination of physical properties of the Eta Virginids from the AMOS Solar Sky Meteor observations. So, Tomas, I said again, like before, it's 17 minutes that are starting now, and it's good if you finish a couple of minutes earlier so we have time for questions. Thank you.
Now you hear me? Okay. Hi, everyone. My name is Tomas Voros. I come from the Communist University in Bratislava, Slovakia, where I am a PhD student under supervision of Juraj Toth. And as Paco said, I will be talking about Eta Virginids and our all-sky observations. Our motivation is hidden in the name of this presentation. It is to determine the physical properties of meteoroids, namely mass, initial mass, bulk density, material strength, ablation coefficient, for example. That is nice, but since we know there are meteoroid streams, they have parent bodies, sometimes known, sometimes unknown, but these meteoroids were once part of that parent body. So by learning about meteoroids, we learn about their parent bodies as well. So we can have a pretty good estimate of the properties of some comets without having to visit them by space probes. And our work can have a planetary defense implication as well, because, you know, the Earth crosses the meteoroid stream, and there is a parent body close to the stream or within the stream, so we can cross the path of that huge parent body as well, but we would know that in advance. But no one knows whether there are some meter-sized or 10-meter-sized fragments. So if we know that, let's say, I don't know, lyrids, they are weak and fragile, maybe we should not be that much afraid of larger fragments, maybe. So this is our instrument. It's called AMOS. That is short for All-Sky Meteor Orbit System. And it records videos of almost, where's the laser? Almost all sky videos at 20 frames per second. And the limiting magnitude for moving objects is +4, around +4. Here it is pictured at our astronomical and geophysical observatory in Modra, close to Bratislava. During the day, we see that the outer shell is closed, but once the sun sets and there is clear sky, such as here above Hawaii, it opens and optical part of the system starts observing. It observes meteors, right? But what do meteors look like actually? If we have some small meteoroid, it enters our atmosphere, starts heating up, and due to high temperature, it starts evaporating, and the vapors start glowing with what we observe. But as we have already heard, there is some dynamical pressure acting on the surface of the meteoroid, so it actually starts to crumble. So some more advanced model looks like this, where we have more fragments and they glow all together. And I must say that the single body model has a huge advantage, that it is really simple, but maybe too simple, because oftentimes we cannot reproduce our observations using the simple model. And sometimes even the results are, well, we cannot interpret them physically, so the results are weird. So now the model with fragmentation is closer to reality. It does not have these issues as often. And I can say that it is closer to reality because we observe the so-called erosion, which is the release of those small grains from the main body. This moving image was made by cropping each frame of our all-sky footage and centering it so that meteor head is always in the middle. And you see a nice wake of those small grains that are released from the surface. This model of so-called meteoroid erosion was devised by Jiří Borovička and his colleagues in 2007, where, as I have already mentioned, there's one main body, which is fragmenting and evaporating. And those small grains behind are so small that we assume that do not fragment any further. So they are treated as single bodies in our simulation. Our observation looks like this. On the horizontal axis, we have time, or at the top there is height. And the left plot shows the measured absolute magnitude, and on the right-hand side, there is measured speed. The points are either blue or orange, so this is a double station observation. Each station has its own color. And additionally, through the measured absolute magnitude, we have plotted the smoothing spline because we have modified the model of meteoroid erosion slightly in a way that in each time step of our numerical simulation, we calculate how many grains must be released so that our modeled magnitude fits the observed magnitude. And by observed magnitude, I mean this smoothing spline. So how does the result of simulation look like? Like this. We have found a good set of physical parameters that reproduce the observation. And as I said, our modification basically works. We have created the light curve that goes perfectly through the observed magnitude. As for the speed, if anyone has ever tried to calculate the speed from video frames, it's relatively tricky. So, but I have put it here because it's easier to imagine the speed, like what is happening. But when we are trying to find the solution, the set of physical parameters, we are looking at absolute magnitude and position, not speed, but position. And by position, I mean the so-called lag, which is defined as which is shown on the left plot, and it is defined as the difference between distance traveled by the real observed meteoroid and the fictitious non-decelerating meteoroid. So what this plot is trying to tell us is that as the meteor was flying, it traveled around 1.5 kilometer shorter distance simply because it was decelerated by the atmosphere. And on the right-hand side, we see residuals. This is how a good fit should look like because even though there is some noise, there is no visible offset either to upwards or downwards. So we performed this simulation, but we cannot do this for all meteors because, as I mentioned, there is noise. That is due to our position measurement precision, and we require that the lag is much larger than the noise simply because we want to know that what we observed is deceleration and not just some random noise. So usually the longer the meteor is, the larger lag is, and therefore it is more likely that we will be able to model this luminous phase. And so we can go to ETA Virginids. They are active every March. And interestingly, their activity is increased several times every 4 years. So it was for the first time noticed quite recently. The increased activity was in year 2009, 13, 17. That is from the Sonota code database. Our Czech colleagues did work on this shower in 2021, and they went a little bit further than just simply observing and counting ETA Virginids, but calculated the PE parameter, which based on not only on entry speed and terminal height, but these two observed values can be related to material strength, and their results show that ETA Virginids are possibly an asteroidal shower because the PE parameter corresponds to high bulk density and compact material. So using simple math, we have determined that this year, there would be another increase in activity, which we have indeed observed above Slovakia, Hawaii, and Chile. We started with more than 1,000 of meteor recordings. Juraj has seen them all. Simply by eye, he judged whether the meteor appears to come from the direction of Eta Virginid radiant. And this way, he found around 100 multi-station meteors that are possibly coming from the radiant of Eta Virginids. Then I looked at these 100 multi-station meteors and chose only those that are long enough. So they may have a chance to decelerate significantly, more than random noise. And 25 of those meteors were, I guess, long enough. So I computed their orbits and found that 16 of them were Eta Virginids, and 4 of them were members of some wider Virginid complex, but not exactly Eta Virginids. And finally, I looked at the positions during the luminous flight, and the lag was sufficiently large in 8 cases. So the initial optimism of 1,000 meteor recordings reduced to 8 Eta Virginids. And this is an example of Eta Virginid. We have already seen these plots. So it was Eta Virginid that entered our atmosphere at the speed of 31.6 kilometers per second, and it was observed between 95 and 67 kilometers above ground. And what did the meteoroid look like? Well, these values reconstructed the position perfectly. So the meteoroid most likely had initial mass of 0.7 grams and bulk density 1,320 kilograms per cubic meter, which means that if it had spherical shape, its size would be 1 centimeter. The ablation coefficient tells us that if the meteoroid receives 1 megajoule of energy, then 0.012 kilograms of that material would evaporate. And the mass of those small grains that are released from the surface of main fragment is just 10 to the minus 8 kilograms. So this is as an example. And together we have masses in a relatively wide range, but I must say that the most massive one, Meteor, was an outlier. Actually, 5 Eta Virginids ranged from 0.5 to 2 grams. The bulk densities are, again, in a relatively wide range. And as I showed the result of one of the previous works that suggested that Eta Virginids may be asteroidal. So for reference, this is the bulk density of ordinary chondrites that we can find on the Earth. So Eta Virginids are most likely not the most compact material we know. But compared to Geminids, which are often called an asteroidal meteor shower, the Geminids are on the lower end of our interval. And what we have also noticed is that the erosion, so the number of those small released grains, is smaller than in cometary meteors that we have previously analyzed, which means that Eta Virginids are less crumbly than cometary meteors, which are very weak. So to summarize my presentation in one table, this is it. I don't know about you, but this looks pretty asteroidal to me. So thank you for your attention.
Okay, thank you, Tomas. We have time for questions. Okay, I first saw Regina.
According to MDC, there is one potential parent body from the asteroidal suggestions. Maybe you can look at it, assuming it dynamically, of course, fits. Yeah, but at least just to see if your results are in any way close to what we know about that asteroid, just like a general check.
Okay. Thank you.
Okay, thank you. We have another question.
For someone who works on the other extreme of very small meteors, this is very interesting, so thank you. On page 14 or 15, I believe it was, you have a lot of structuring in your predicted 14. Yes, when you look at your model predicts a lot of structuring of your ablation absolute magnitude. What's responsible for that? The model must have quite a lot of complexity to get something like that.
Well, we want to fit the smoothing spline, so it depends on what smoothing parameter we choose. It can be either very like trying to go through all these measured points, so it will be like this, or we can make it really smooth. We tried several values of smoothing parameter, and the results did not change in any significant way. So some maybe oscillations, they averaged.
Oh, so this is flying through many simulations with
this is just
different
through
guesses.
observation.
What?
Through observation. It is firstly
Now I'm quiet. But I think, as I understood the question, it was what was the reason for the changes in the light curve, kind of the fragmentation processes, number of the mass and grain size involved in this light production.
well, the erosion, the release of those small grains. I don't have the plot of how many grains are released in time, but it was not constant. So some maybe internal inhomogeneity, maybe. Somehow, yes, because we calculate how many grains must have been released in order to fit the observation. So implicitly, yes.
Okay, thank you, Tomas. We ran out of